Welcome to the deep dive. Today, we're going to be checking out turboprop engines, and this one's especially for you because you're interested in how they work and, how they compare to those good old piston engines. Yeah, get ready for some interesting stuff because turboprops are really cool.
They are.
They blend the power of a jet engine with the efficiency of a propeller.
Yeah, it's a pretty cool combo.
It is a pretty cool combo. So let's jump right in. I guess the place to start is that both piston and turbine engines are internal combustion, right? They both burn fuel and air to make power, but I've heard the process is pretty different. So what's the big difference?
You're absolutely right. The main difference is that gas turbines, they operate continuously, unlike piston engines, which rely on distinct strokes.
Hmm.
So to make this a little bit more clear, imagine a piston engine as a bicycle pump. You have those separate actions for intake and compression and combustion and then exhaust.
Right.
Now, picture a turbine engine as a hairdryer. A constant flow of air powers the whole process.
Okay. I can see that. So how does that continuous flow work in a turbine engine?
It's kind of a beautifully orchestrated cycle.
Okay.
So it starts with air getting sucked into the intake, and then it gets compressed to become hot and dense.
Right.
Then fuel is injected and ignited that creates a powerful blast of hot gas, and that gas expands and spins a turbine, which is connected back to the compressor at the front.
So it's like a self-sustaining cycle. The exhaust gas powers the turbine, which pulls in more air, and the whole thing just keeps going.
Exactly. And here's something pretty cool.
Yeah.
Not all that compressed air goes to combustion.
Oh.
Some of it is what we call bled off for other purposes, like de-icing wings or pressurizing the cabin.
Oh, wow. That's awesome.
Talk about multitasking, right?
Yeah, that's really cool. It sounds like they really, got every little bit of utility out of that airflow. So let's talk about turboprops specifically. They're kind of like the hybrid cars of the aviation world, right? Combining the best of both worlds.
That's a great analogy. Turboprops blend the high speed and altitude capabilities of jets with the excellent takeoff and climb performance of propeller-driven planes. It's like having a powerful engine for high-altitude cruising and an efficient one for getting up there quickly.
Sounds like a win-win. So what other advantages do turboprops have over piston engines?
Well, for starters, they're lighter.
Okay.
They're more reliable and known for their smooth operation
Okay.
with minimal vibration.
Yeah.
And of course, that propeller, that's a game changer for takeoff and landing.
Yeah, I mean, there's a reason they're used in all different kinds of aircraft. I've heard that turboprops have a sweet spot when it comes to speed and altitude. Is there a range where they're the most efficient?
Absolutely. They really shine at speeds between 250 and 400 miles per hour
Right.
and altitudes from 18,000 to 30,000 feet.
Oh, wow.
That's where their combination of power and efficiency really makes the difference.
Okay, that makes sense. Now, I know this might get a little bit technical,
Sure.
but I'm curious about how we measure power in turboprops. Piston engines use horsepower, but it's different for turboprops, right?
You are right. With turboprops, we talk about shaft horsepower, or SHOP. It's not just about the engine's power, but also the torque it generates, that twisting force on the propeller shaft.
So it's a more accurate representation of the power delivered to the propeller.
Precisely. Shaft horsepower gives us a more complete picture, and it's essential for understanding how a turboprop performs. And here's a little bonus.
Okay.
Turboprops also produce a small amount of jet thrust from their exhaust, usually less than 10%. Not a huge amount, but every bit helps.
So it's like getting a little extra push from the exhaust gases.
Yeah.
I like it. Okay, so we have this powerful gas turbine spinning a propeller, and we're measuring the power in shaft horsepower, but how much of the actual thrust is coming from the propeller itself?
At sea level, that propeller is doing the heavy lifting. It accounts for about 90% of the total thrust. Remember, we talked about propellers being great at low speeds?
Right.
They can accelerate a massive amount of air even when the plane is moving relatively slowly, which makes them incredibly effective during takeoff and climb.
Okay, I'm starting to see how all these pieces fit together. So we've got the continuous power of the turbine engine combined with the low speed efficiency of the propeller, all measured in shaft horsepower. That's a pretty powerful combination, but I want to make sure we're clear on terminology. We're talking about turboprops, not turbo-supercharged engines, which are a completely different thing.
That's an important distinction. Turbo supercharging is a way to boost the power of a piston engine,
Right.
while turboprop is a completely different type of engine altogether. It's important not to confuse the two.
Good point. So we've established that turboprops are powerful and efficient, especially at certain speeds and altitudes. But here's a question that's been on my mind. How does altitude affect a turboprop's fuel efficiency?
This is where things get really interesting. Well, a turboprop's power output decreases with altitude, just like any engine. Its fuel efficiency actually increases as you climb higher.
Wait, so you're telling me they get more fuel efficient the higher they go? That seems kind of counterintuitive.
It might seem that way, but it all comes down to the propeller and the thinner air at higher altitudes. The propeller is actually more efficient in thinner air, allowing it to convert more of the engine's power into thrust.
So it's like the propeller gets a performance boost at higher altitudes because of the reduced air resistance. That's a pretty neat trick.
It is, and it's one of the reasons why turboprops are so well suited for certain types of flying, like regional airliners and cargo haulers that operate at those higher altitudes.
Yeah.
But it's important to remember that turboprops, like any complex machine, have their operational nuances. One of the big ones is understanding the importance of operating within the engine's limits.
Okay, let's talk about that. What are some of the key things to keep in mind when it comes to operating a turboprop safely and efficiently?
Unlike piston engines, turboprops have very specific limits on temperature, rotational speed, and torque exceeding those limits, even for a few seconds, can cause serious damage to the engine. It's like pushing a race car too hard. You might get a burst of speed, but you risk blowing the engine in the process.
So it's all about respecting those limits and understanding how different factors can affect them. I imagine things like weather conditions play a role, right? A hot day versus a cold day could change things.
Absolutely. Temperature is a key factor in determining which limit is reached first on a scorching day. You might hit the temperature limit before the torque limit, and vice versa on a chilly day. Pilots need to be aware of these environmental factors and adjust their operation accordingly.
It's like a constant balancing act, making sure you're getting the most out of the engine without pushing it beyond its limits. Now, I know there are different types of turboprops out there. What's the difference between a fixed shaft and a free turbine engine?
Think of them as two different ways of achieving the same goal-efficient and powerful propulsion.
Okay, I'm intrigued. Let's start with fixed shaft engines. What's the basic design?
In a fixed shaft engine, the propeller is directly connected to the engine's main shaft. They're essentially locked together, spinning at the same speed. A classic example is the Garrett TPE 331 engine.
So it's a very direct connection between the engine and the propeller. What are some of the implications of that design?
One important consideration is that if the engine fails in flight, the propeller can create a lot of drag as it windmills in the airstream. Remember, that compressor at the front of the engine needs power to keep spinning.
Right.
And a windmilling propeller can actually act like a brake, creating drag and reducing your aircraft's performance.
That sounds like a potential problem, especially in a twin-engine aircraft where you lose one engine.
Exactly. That's why fixed-shaft turboprops are often equipped with a safety feature called negative torque sensing, or NTS.
Okay, what does NTS do?
NTS acts like a safety net for your propeller. It constantly monitors the torque on the propeller shaft if the engine loses power. NTS senses that the propeller is now driving the engine instead of the other way around to prevent that drag we talked about. It automatically feathers the propeller, essentially turning it into a weather vane so it slices through the air with minimal resistance.
That's a pretty ingenious solution. So tell me about free turbine engines. How do they differ from fixed shaft engines?
The key difference is that in a free turbine engine, the propeller is driven by a separate turbine. This means the propeller can be feathered without actually shutting down the entire engine. The Pratt & Whitney PT6 is a great example of a free turbine engine.
So it's like having two engines and one to drive the compressor and one to drive the propeller.
That's a good way to put it. They're not completely separate engines, but they do operate independently. This design offers several advantages. For instance, the propeller can spin at its own optimal speed, regardless of what the engine is doing, which can improve efficiency.
That makes sense. It sounds like free turbine engines offer a bit more flexibility and control. What about the accessory drive on these engines? What does that do?
Good question. The accessory drive, typically located at the back of the engine, powers essential components like fuel pumps, oil pumps, and the starter generator. The speed of this drive, referred to as N1, gives us a direct indication of the compressor speed. Think of N1 as the heartbeat of your compressor section. By monitoring it, you can tell how hard the engine is working and make sure it's operating within safe limits.
So N1 is a crucial parameter for monitoring engine health and performance. Now, I'm curious about the cockpit controls and instruments for turboprops. Are they drastically different from what a piston engine pilot might be used to?
There are definitely some key differences, and it's important to understand how they work. We can dive into that further in the next part of our deep dive.
Sounds good. We've covered a lot of ground in this first part, from the basics of gas turbine engines to the differences between fixed shaft and free turbine turboprops. It's clear that these engines have a lot to offer in terms of power and efficiency, but they also come with their own set of operational considerations.
We've barely scratched the surface, but I think we've given you a good foundation for understanding how these fascinating machines work.
Stay tuned for part 2, where we'll delve into the cockpit controls and instruments, explore the unique capabilities of turboprops like reverse thrust, and discuss some of the challenges of transitioning from piston engines to turboprops. Welcome back to the deep dive. Last time we really got into, how turboprops work, from that continuous gas turbine cycle to the different types of engines out there. And now I'm ready to step into the cockpit, so to speak.
Okay.
What are the controls and instruments like in a turboprop aircraft?
Well, it's definitely a different experience compared to your typical piston engine aircraft.
Okay.
So let's start with fixed shaft engines, since those are what you're likely to encounter first if you're transitioning to turboprops.
Okay. Sounds good. What are the main controls we'd find in a fixed shaft turboprop?
You'll have a power lever, much like a throttle in a piston engine. But instead of controlling fuel flow directly, it controls how much fuel is entering the combustion chamber. And then there's a condition lever.
So the power lever, dictates how much oomph you're giving the engine. So what about that condition lever? What does that do?
The condition lever is basically setting the desired engine RPM.
Right.
In a fixed shaft engine, the engine and propeller are directly connected, so they spin at the same speed. The condition lever makes sure that the engine stays within its safe operating range.
Got it. So we've got our power lever and condition lever. What instruments are we looking at to monitor engine performance in a fixed shaft turboprop?
There's a few key gauges you'll want to keep an eye on.
Okay.
First, you have your torque or horsepower gauge that tells you how much power the propeller is getting.
Okay.
Think of it as your power output meter.
Okay. That one seems pretty straightforward. What else are we watching?
Next up, there's the ITT gauge. It stands for inner turbine temperature. This little guy is like the engine's temperature watchdog, measures the temperature of the exhaust gases between stages of the turbine. And it's crucial for, making sure you don't overheat things.
Yeah, you got to stay within those temperature limits we talked about earlier. What other instruments should we be aware of?
You'll also have a fuel flow indicator, tells you how much fuel you're burning.
Yeah.
An RPM gauge for the propeller that lets you know how fast that prop is spinning.
Yeah.
Pretty self-explanatory, right?
Yeah, those make sense. Now, what about free turbine engines? What are the controls and instruments like in those aircraft?
With free turbine engines, you have 3 main controls.
Okay.
A power lever, a propeller lever, and a condition lever.
Okay, so we have a separate lever just to control the propeller speed. Why is that?
Well, because in a free turbine engine, the propeller is driven by its own separate turbine. So this gives you more precise control over propeller speed, independent of the engine speed.
Okay, I see how that could be useful. So what does the propeller lever actually do?
It lets you fine-tune the propeller's pitch, which is the angle of the blades.
Okay.
By changing the pitch, you can control how much thrust the propeller produces.
So it's like having more control over, how much bite the propeller has on the air.
Yeah, that's a great way to put it.
Okay.
And the condition lever in a free turbine engine, similar to the one we talked about in the fixed shaft engine, is essentially an on-off switch for fuel delivery.
Okay, so we got those 3 levers to play with on a free turbine engine. What about the instruments? Anything new and exciting to monitor?
You'll still have your ITT gauge, fuel flow indicator, and oil temperature and pressure gauges, just like in a fixed shaft aircraft.
Okay.
But there are a couple of extra instruments that are specific to free turbine engines.
Okay.
One is the torque meter. It measures the twisting force going to the propeller shaft.
Okay.
And then you have a separate propeller tachometer to monitor the propeller speed, since it's not directly tied to the engine speed anymore.
Makes sense. So it seems like turboprops, regardless of whether they're fixed shaft or free turbine, have, kind of a more complex set of controls and instruments than piston engines. It must take some time to get used to managing all that.
It definitely does. But once you get the logic, it becomes second nature. And, the added complexity comes with some huge benefits in terms of performance and efficiency.
Speaking of performance, one thing that always gets me about turboprops is that reverse thrust.
Yeah.
Something that piston engine pilots, can only dream of. Can you explain how that works?
It's a pretty neat trick. It all comes down to the angle of the propeller blades.
Okay.
By changing the pitch angle, that is the angle at which the blades are slicing through the air, we can actually use the propeller to generate thrust in the opposite direction. basically acting as a brake.
Wait, so the engine isn't actually running in reverse?
Nope. The engine keeps spinning in the same direction. It's the angle of the propeller blades that changes, redirecting that airflow forward instead of backward.
Oh, wow. Okay.
And it's all controlled by the power lever.
So you move the power lever past the idle position, and that's how you engage reverse thrust.
Exactly. We call this the beta range. As you move the lever further into beta range, those propeller blades flatten out, eventually going past flat pitch and into negative pitch that results in that reverse thrust effect, allowing you to slow down on landing or control your taxi speed.
I've heard that beta range can be kind of tricky to manage. Is it something that takes a lot of practice?
It takes some finesse for sure,
Yeah.
but it's a powerful tool once you get the hang of it. Think of it like this. You're not just controlling the engine anymore. You're directly controlling how much thrust the propeller is making.
That makes sense. It sounds like mastering turboprop operations requires a whole new level of understanding and coordination
You're right.
compared to flying, a piston engine aircraft.
There's definitely a learning curve, but that's part of what makes flying turboprop so rewarding.
Oh, okay.
It's a challenge that pushes you to be a better pilot.
Now, I know we can't dive too deep into electrical systems,
Sure.
but I'm kind of curious about the basics. What kind electrical system do most turboprops use?
The typical setup is a 28-volt DC system powered by batteries and starter generators.
Yeah.
It's not too different from what you'd find in a piston engine aircraft,
Okay.
but there are a few unique features.
Okay. Tell me more what's special about the electrical system in a turboprop.
Well, for one thing, the starter generator is a real multitasker.
Okay.
It acts as both a starter motor to get the engine going and then a DC generator to provide electrical power once the engine's running.
So it's like a 2-for-1 deal.
Exactly.
That's pretty efficient. What about inverters? Are those used in turboprops?
Absolutely. Some of that DC power generated by the starter generator is converted to AC power using an inverter. And you need that for certain avionics and other systems that require AC power.
Okay, so we've got batteries, starter generators, inverters. How does all that power get distributed throughout the aircraft?
It's all done through a network of power distribution buses. They ensure that power gets where it needs to go and that the system is protected from, overloads or short circuits.
Okay.
Think of them as the electrical highways of the aircraft.
So these buses are like traffic cops directing the flow of electricity, keeping everything running smoothly. What about redundancy? Are there backup systems in case something fails?
Absolutely. Multi-engine turboprops usually have, multiple power sources and buses so that if one fails, the others can take over. Redundancy is super important in aviation, especially when you're talking about aircraft operating at higher altitudes where reliability is paramount.
That makes sense. Now, I'm guessing there are some unique operational considerations for pilots who are transitioning from piston engines to turboprops. What are some of the things that might catch a pilot off guard if they're not prepared?
Yeah, you're right. Flying a turboprop is definitely a different experience, and there are a few things that can take some getting used to. One of the most noticeable is the potential for power lag, especially with free turbine engines.
Power lag? What's that?
It means there's a slight delay between moving the power lever and the engine actually giving you the power you asked for.
Oh.
It's not as instantaneous as a piston engine.
So you can't just, jam the throttle forward and expect an immediate response.
Exactly. You need to anticipate those power changes and lead them a bit more than you would in a piston engine. And this is especially important when you need a quick burst of power, like during a go-around or a low-altitude maneuver.
So it's all about being proactive and planning ahead. What other quirks should transitioning pilots be aware of?
Another big one is the sensitivity of turbine engines to heat.
Right.
Remember those temperature limits we talked about? Exceeding them, even for a short time, can have pretty bad consequences.
Yeah, so hot starts are something to be very wary of.
Absolutely. A hot start happens when the engine temperature spikes during startup, and it can happen really quickly. So pilots need to be really careful watching those temperatures and be ready to shut down the engine if things start to get out of hand.
And what about those hung starts I've heard about?
A hung start or a false start is when the engine doesn't accelerate as fast as it should during startup.
Okay.
It can be caused by, low battery power, a problem with the starter, or even fuel flow issues.
So it's basically a sluggish start that could lead to bigger problems.
Exactly. And remember, we can't just, slam the power lever forward on takeoff like you might in a piston engine. Takeoff power in a turboprop is often limited by either torque or temperature. So it's important to follow established procedures for a safe and efficient takeoff. Rushing things can lead to exceeding those limits, which is never a good thing.
Right. So standardized procedures are even more critical in turboprops.
Absolutely. The increased complexity of these aircraft means that, sticking to routine is essential for safety and efficiency. It's not just about knowing how the engine works.
Yeah.
It's about understanding how to operate it within its limits and according to best practices.
Okay, one last question before we move on. What about high altitude operations? What unique challenges do turboprops face up there?
The biggest factor is the thinner air at higher altitudes. This affects engine performance, and pilots need to understand how it impacts things like power output and fuel consumption.
So it's not just about flying higher, it's about understanding how the environment changes up there
Yeah.
and how to adjust your flying techniques.
That's a great way to put it. Turboprops are incredible machines, but they demand a certain level of respect and understanding to operate them safely and efficiently, especially at those higher altitudes where the air is thin.
Well, I think we've covered a lot of ground in this second part of our turboprop deep dive.
Yeah.
We've gone from the cockpit controls and instruments to the nuances of power management and the importance of, standardized procedures.
And we've only just begun to scratch the surface.
Yeah.
But I think we've given our listeners a solid understanding of what it takes to fly a turboprop safely and efficiently.
Stay tuned for part 3, where we'll dive into the world of turboprop emergencies, exploring those what-if scenarios that every pilot needs to be prepared for. We'll talk about engine failures, propeller malfunctions, and, other situations that can really test your skills and knowledge.
It's the part of aviation that nobody wants to think about, but being prepared for emergencies is what separates good pilots from great ones.
So buckle up, listeners. We're going to take you through some scenarios that'll really make you think on your feet and make the right decisions under pressure. See you back here soon for the final part of our turboprop adventure.
Welcome back to the deep dive.
Yeah.
We've spent the last 2 parts really digging into how turboprops work and all their unique features and even what it's like to be in the cockpit, managing those powerful engines. But, we've got to talk about the one part of aviation we all hope to avoid, but absolutely have to be prepared for emergencies.
Yep.
You're absolutely right. Emergencies are part of flying, and turboprops, with all their complex systems, they definitely have some unique challenges, but we're not here to scare you. We want to give you the knowledge to handle those what-if scenarios safely and effectively.
Okay, good to hear. So let's not sugarcoat it. What are some of the most common emergencies that turboprop pilots face?
One of the most critical and thankfully rare is an engine failure, especially in a single-engine aircraft.
Yeah, I can see how that would be, top of mind for anyone flying with just one engine. What are the immediate actions a pilot should take if that engine quits?
The very first thing is maintaining control of the aircraft. You just lost a lot of power, so you need to adjust your pitch and airspeed to keep a safe glide. Remember those basic airmanship skills we all learned: aviate, navigate, communicate.
Right, those are the fundamentals that can save your bacon in an emergency. So once you've got the aircraft under control, what's next?
Then you can start troubleshooting the engine problem. Maybe it's something simple like a fuel flow issue, that you can fix, or maybe it's a more serious problem and you need to find a place to land. Either way, the aircraft's emergency checklist will tell you what to do.
Right, those checklists are gold in an emergency. They help you stay calm and methodical when things are getting a little hairy. So we talked about engine failures. What other emergencies should turboprop pilots be ready for?
Another one that can be pretty challenging and maybe a little unnerving is a propeller malfunction.
Okay, yeah, I can see how that would get your attention. Are we talking about a runaway prop? Those sound terrifying.
A runaway prop is one possibility. It happens when the propeller governor fails and the propeller spins out of control at really high speed. It can happen from a mechanical problem or even something as simple as a bird strike that damages the governor.
That sounds like a nightmare. What can you do if that happens to you?
In most turboprops, there's a procedure for feathering the propeller, basically stopping it from spinning and reducing drag.
Right.
It might sound counterintuitive, but sometimes the best way to get control is to stop that prop from windmilling.
So it's like hitting the emergency brake for a runaway propeller.
That's a good way to put it. It takes some quick thinking and action, but it's a skill every turbo pilot needs to know. But even with a feathered propeller, you're still going to lose some performance, so you need to adjust your flight plan.
Makes sense. What other propeller problems might we see?
Another is a propeller overspeed, where the propeller goes faster than its maximum RPM.
Yeah, I would imagine that could cause some serious vibrations, maybe even damage.
Yeah, you're right. An overspeed can cause a lot of vibration, and that can damage the propeller and even the engine. It's usually caused by a problem in the propeller governor or a sudden change in air density, like flying into a microburst.
So what's the best way to keep a propeller overspeed from happening?
Good power management. is key pilots need to know the propeller's limits and not exceed them, especially during critical phases of flight.
And if it happens, what should you do?
The first thing is usually to reduce power and follow the checklist. It'll guide you through the steps to get the propeller speed back to normal.
Okay, so we've got engine failures, propeller issues. What other emergencies are out there in the turboprop world?
Another one, especially at higher altitudes, is a pressurization problem.
Ah, yeah. Keeping the cabin comfortable and everyone breathing is pretty important up there. What can cause a pressurization problem?
There are a few things. It could be a leak in the cabin or a problem with the pressurization system or even a rapid decompression at high altitude. Whatever the cause, it needs attention right away.
So if you feel your ears popping and the cabin pressure is going down, what's the first thing you do?
Oxygen masks. You and your passengers need oxygen, especially at high altitude where the air is thin.
Great. Don those masks, everybody, and then what, get down to a lower altitude?
Absolutely. You need to start an emergency descent to get down to an altitude where you don't need the extra oxygen.
And I'm guessing there's a checklist for this.
You bet. Every turboprop will have a checklist for a pressurization problem. It will tell you exactly what to do for a safe descent and help you figure out what's wrong.
Okay. Engine failures, propeller issues, pressurization problems, anything else?
Well, one that's not as common but still worth mentioning is a fire.
Okay, fire on an aircraft, that's not a mental picture I enjoy. Where are these fires most likely to happen?
Most likely in the engine compartment or the electrical systems, it's serious. But aircraft are designed with fire detection and suppression systems to help.
So what do you do if there's a fire?
First, you need to figure out where the fire is. Then you follow the fire checklist, which will usually mean shutting down the engine or system that's on fire and using the fire extinguisher.
Sounds like you need to think fast, act fast, and know those procedures.
Exactly. And remember, in any emergency, talking to people is important. You need to keep your passengers informed, talk to air traffic control, and if you have to declare an emergency.
So it's not just flying the plane, it's managing the whole situation, keeping people informed, and making sure everyone stays calm.
That's it. A good pilot isn't just a good flyer. They're a good decision maker and communicator, especially when things get tough.
Well, we've covered a lot in this final part of our turboprop deep dive. I think we've looked at some scenarios that can really get your heart racing.
But as we've talked about, with the right knowledge and training and respect for these machines, turboprop emergencies can be handled safely.
I hope our listeners have enjoyed this turboprop deep dive. It's been informative and engaging and maybe even a little bit empowering.
We went from understanding how these engines work to knowing how to handle even the toughest situations. It shows how creative people are and how dedicated they are to keeping our skies safe.
That's a great way to put it. Thanks for joining us on this turboprop adventure. We'll see you next time on The Deep Dive, where we'll take you on another journey into the fascinating world of aviation.